Choosing a blockchain platform is an architecture decision, not a popularity contest. In this module, we'll compare public, permissioned, consortium, and hybrid options through the lenses of compliance, privacy, scalability, and integration. Then we'll connect those trade-offs to issuance, settlement, custody, and tooling choices. So far, we've built the foundation: market context, enterprise architecture, stakeholder flows, and the major network models. Now we move from deployment patterns to platform choice, comparing leading options for regulated issuance before turning to tooling and selection methods. Before choosing a blockchain, apply the same lens to every candidate. Start with the asset. A security, fund, stablecoin, real-world asset, or payment token may require very different capabilities. Next, test control requirements such as permissioning, privacy, compliance rules, governance, and node operations. Then assess technical fit: contracts, finality, scale, tooling, custody, and APIs. Finally, confirm enterprise readiness through audits, support, security, and real production history. Think of the EVM ecosystem as a shared operating model for tokenized assets. Ethereum, Polygon, Avalanche C-Chain, and Besu can use familiar standards like ERC20, ERC721, and permission token patterns. They also benefit from mature Solidity tooling, wallets, custodians, explorers, and audit practices. The real design choice is not simply EVM or not. It is which EVM environment best fits your requirements for liquidity, fees, finality, validator governance, privacy, compliance, and operational control. Ethereum's advantage is not just the chain itself. It is the surrounding ecosystem: mature smart contract standards, deep liquidity, wallets, custodians, auditors, and developer tools. That makes it strong for public tokenized assets, stablecoins, and institutional DeFi connectivity. Regulated issuance, however, usually needs extra layers: identity checks, permission transfers, compliance registries, and governance outside the chain. The trade-off is clear. Ethereum offers trust and interoperability, while teams must manage gas costs, visible data, throughput limits, and public network dependency. Polygon is attractive because it keeps the Ethereum developer experience while moving many transactions to cheaper, faster networks. Teams can reuse Solidity, wallets, and token standards, which reduces launch friction for loyalty points, collectibles, retail assets, and high-volume transfers. But lower cost is only part of the decision. Each Polygon option brings questions about bridge design, validator assumptions, custody support, compliance tooling, and liquidity. For institutional tokenization, those trust and governance details matter as much as fees. Avalanche separates EVM access from network customization. The C-Chain lets teams deploy Solidity contracts with familiar wallets, libraries, and developer tooling, so migration from Ethereum is relatively straightforward. Subnets add another layer. Teams can define validator requirements, governance rules, permissions, fees, and performance assumptions. For institutions, this creates a useful mix of public EVM compatibility and purpose-built control. The trade-off is operational. Validator governance, interoperability, custody, and ecosystem maturity all need careful evaluation. Besu gives enterprises an Ethereum-compatible client without forcing every deployment onto the public chain. The same Solidity contracts and EVM tooling can support a permission consortium where issuers, custodians, agents, administrators, and observers run controlled nodes. Here, the main issue is governance. You gain configurable consensus, private transactions, and access controls, but you must define validator onboarding, upgrades, monitoring, incident response, and compliance ownership before the network carries regulated assets. Enterprise DLT is less about open public execution and more about controlled collaboration between known institutions. Fabric emphasizes permission networks and flexible access control. Corda focuses on bilateral workflows, where only the parties to a deal see the relevant facts. Canton-style architectures extend that idea towards synchronized financial contracts across domains. The key design question is fit. Who can join, who can see data, how contracts execute, and how legacy systems connect. Hyperledger Fabric is built for networks where participants are known, but trust still needs structure. Organizations join through managed identities, run chain code for shared business logic, and agree on transactions using endorsement policies. Privacy is handled with channels and private data collections, so not every member sees every record. That makes Fabric useful for supply chain, trade finance, and asset registries, especially when blockchain workflows need to connect back into ERP and other enterprise systems. Corda and Canton-style designs begin with a different assumption. Financial contracts are private by default. Instead of broadcasting every transaction to a whole network, the relevant counterparties share the contract state and rules, while a notary or synchronizer prevents double spends and orders events. That makes these designs useful for bilateral agreements, post-trade settlement, and regulated institutional networks. The architecture challenge is mapping legal obligations into code, onboarding trusted participants, and connecting safely to token platforms. Stellar is built around payment movement rather than broad smart contract execution. A typical flow starts with fiat entering through an anchor, becoming a tokenized cash or stable asset, moving quickly across the ledger, and then being redeemed through another off-ramp. That makes Stellar attractive for remittances, stablecoin settlement, and straightforward issuance. For tokenized securities, the hard work is compliance. Issuer controls, identity checks, transfer limits, custody, monitoring, and reliable wallet and fiat ramp integrations. Solana is best understood as a performance-first network, not simply a cheaper alternative to Ethereum. Its throughput and low fees can make high-volume payments and consumer asset flows practical. That advantage, though, comes with design decisions architects must test. Smart contracts use a different development model, often Rust and Solana-specific tooling. For institutional use, validate custody, compliance, analytics, validator resilience, and operational history. The right question is whether Solana's speed matches your controls and integration requirements. Across all of these options, platform choice remains a fit decision. Public EVM networks work well when standards, liquidity, composability, and custody support matter. Permissioned or enterprise DLTs fit workflows that need consortium governance, privacy, and tighter operational control. Payment-oriented networks can be compelling for stablecoin settlement or high-volume transfers if compliance and custody requirements are met. A sound selection should end in documented trade-offs, risk assessment, and an architecture decision record. No blockchain platform is best in isolation. EVM chains bring standards and tooling. Enterprise DLT brings permissioning and privacy. Payment networks emphasize speed and cost. Next, we'll turn these comparisons into practical tooling choices and a defensible platform selection framework.